Okay, today is September 28, 2021, and let's talk about the syllabus and the upcoming exam that we're gonna have. We already covered the material for the first exam. Here is the syllabus. The syllabus has already been uploaded to the shareable folder in the Google Drive. Let's see what's going on here. It's not recording, huh? No, I think it's okay. Let's see here. Okay, yeah, it is recording. Good. Okay, enable editing. So that was the email that I sent, at least I was supposed to send to you. I do not know why you didn't get it. Okay, so here you go. The, I prefer to do this way because otherwise you're going to spend too much, we're going to waste too much of the lecture time. You won't have enough time to cover everything. So what we're going to do, we are going to come here on October 7th. Right now, the first exam is scheduled for October 7th on a Thursday. Okay, we come here for the lecture, and then the exam is going to be available on Canvas from 7 p.m. to 12 noon the following day. Okay? Can you do the exam within this window? All you have to do is to get 2 hours window. Okay? Make sure you can fit in there. You know that there'll be morning there, and okay. So some of the exams are going to be on Thursday. Since we have 4 partial exams, I'm going to do the following. I'm going to fit 2 partial exams on Thursday and 2 partial exams on Tuesday. Okay? I'm going to even that out for both sessions. Yeah.
So when does it start?
7 p.m. 7 p.m. on October 7th.
October 7th.
So you have until 12 noon of the following day. Okay?
That Tuesday before we're gonna have a lab.
Let me see what I have here. Yes. Uh-huh. You're going to have a lab that Tuesday before. Yes. Uh-huh. The Tuesday before you do have a lab, and the Tuesday following. Okay. So let me see what's going on here. I gotta do something about that. Yeah, I gotta fix that. We cannot have projectile motion twice for the Tuesday session, right? Yeah, I have. Let's see here. How are we gonna do it? Yeah. Okay, I think what I'm gonna do here. Yeah. Very well. You pointed out something very important. Okay. So I gotta fix here the schedule, right? Maybe we would not. Maybe the Tuesday guys are not gonna have this session here. I gotta figure out how to do that. Okay. Let me make sure. Let me see. We do have. Yeah. It looks like we have a lab here. I will think about that. Okay. Until then, until the exam, I'll clear that up.
I only asked because I would want to switch my work day on Thursday to Tuesday
Mm-hmm.
in order to have time to take the exam. But if we have a lab on Tuesday, then I've got to miss work on that Thursday.
I see. Let's see. Well, remember that. Let's see. So you work on Thursday? Is that what you said? Okay.
As soon as I get out of here.
Uh-huh. So you get, and well, I can extend this window. Let's say 7 p.m. to 7 p.m. 24 hours window. Can you fit 2 hours there?
Yeah, that works.
Okay.
Yeah.
7 p.m. to 7. No, 24 hours. I didn't want to do 24 hours, but that's Okay.
I
It's
mean, I
not
don't want to
bad.
be in the meetings, but yeah, because
Yeah.
I'm gonna get out work late and then
Mm-hmm.
I'll take the.
Yeah, yeah. I think it's fair. Yeah, to do a 24-hour window. Okay. I'll do the for the other exams too.
Thank you.
I'll do for the other exams as well.
Professor.
Yeah.
So we're still gonna come in for lecture on 7th of
Yeah.
October?
Mm-hmm.
Okay.
Used to. Let's see. Oh, wait a minute. Here you go. That's the one here. 7 p.m. Yeah, that's right. There will still be a lecture, you know, Yeah, I cannot waste this lecture, okay? Otherwise, we fall too behind in the material. Okay, I was looking into that. It's not going to work out to do it the other way I was telling you. Yeah.
We have a lab tonight.
Yes, we have a lab tonight. Yeah, we have a lab tonight. So where are we right now? We are writing here, 28th. Okay. Vectors and the first table. So that's material for the exam. That's material for the exam. So what's gonna happen here on the 7th? Before the 7th, there is a lab for Tuesday, a Tuesday lab. Um, then on Thursday, we're using the Thursday for the exam. So I'm thinking, I'm thinking what I'm gonna do here. Maybe, yeah, I'm thinking. I guess we're gonna do the following. I don't want to waste this Thursday either. So I'm going to do, yeah, I'm gonna do lab 5. Yeah, let's do it this way. Here you go. For Tuesday, right? Tuesday will be slightly ahead of Thursday. Okay, and then I have to fix the rest. We have only one lab here see that? We have only one here. Actually, we have two. Last day of class. So, but I think it's better to do that. The Tuesday is going to be just momentarily ahead of the Thursday students. And Thursday we do the projectile motion, right? And then I have to fix the rest later on. So now we have version number 5. That's version number 5. And that's version number 5 of the syllabus. The PDF. And I will upload the PDF document there to the shareable folder. Here you go. And so what changed here was the scheduling, right? The scheduling of the lab and the exam. As we go along, I'll be making some other minor adjustments to the schedule. Before COVID, I have everything sorted out. I knew exactly how to do the exams, and then COVID stroke. We split the lab into 2 sessions. Right now, I have to figure out how to do the class to teach this course again with you. But those are some minor stuff. Delete, remove. Okay, and the shareable folder is right in here. Okay, I'm gonna put the version 5 of the syllabus there. I will delete version 4. Okay, that's the version number 4. Okay, so let's just summarize what has changed here. We are going to have an exam, but the exam is going to be during the lab time. Okay, starting at 7 o'clock. The first exam right now is scheduled on October 7th. And it's going to open at 7 p.m. on October 7th. You're going to have a 24-hour window, right? You pick up 2 hours to do the exam within this 24-hour window. Okay, that's how the exams are going to be. I had to do that again. I had to do that because otherwise I'll be losing too much lecture time here and will be falling too much behind. Okay.
So it will have until October 8th at 7?
Yeah, that's right. Yeah. So start at 7 p.m. right, which is already at the end of the day. So you need to. I think it's a good thing to have a morning and an afternoon of the following day for you to with a fresh, to do the exam with a fresh head, right? Okay, and what else do I have to tell you? Okay, I corrected the first lab report. I corrected. Did you get the first lab report? I'm going to brief you how you're going to Physics 37 notes. Sorry you couldn't find the file. Okay, somewhere. Lab lecture. Physics 37. Oh, battery is running low. Forget it. Here are the notes. And again, all partial exams are going to be like that. All partial exams. The final exam, no. The final exam is set at a given day and time. Okay, you have just 2 hours to do the final exam. There won't be any windows there. Okay, so insert. Good. So here we go. Today is September 28th, 21. What changed? Okay, exam 1 is scheduled on October 7, for October 7, comma, there will be a 24 hours window for you to do the exam. Every partial exam will be like that. Every partial exam will be like that. Okay, the final exam, the final exam will be at the scheduled day and time, and you will have only 2 hours to do the exam. You have only a 2 hours window to do the exam, to do the final. Now, what else we have to talk about? We have to talk about, okay, lab report 1 was corrected and posted to your group folder. Okay, and I'm gonna walk you through what you have to do to read that lab report. Okay, to open that lab report. Okay, so here you go. It's not straightforward, but once you get that, you know how to do it. In order to open your corrected lab report, you should do the following. And try to do it right now if you have a computer. Maybe you can do that with your cell phone. I think you can do it with your cell phone as well. You should do the following. 1. Access your group folder. Okay, that's the first step. So let's go there to a group folder, any group folder. Okay, which group wants me to access their folder?
7.
With Tuesday or Thursday?
Tuesday.
Tuesday? Group 7, okay. So if you are group 7, right, you already have a link there, go to your group folder, and here you go. You have 2 files, an HTML file, P37 Tuesday L01, in the case of group 7 is G7, right? And then you have a folder with the same name. Okay? Okay, so here you go. Access your group folder. Okay, access your group folder. 1. Download the following. Download the following. 1. P37. Let's say Tuesday, right? That's for the Tuesday session. L01 group. I'm gonna put group X here, and then it's called folder. No, file underscore file. Download the following. This is a folder. This is a folder. And there is something else you gotta download. P37. Okay. HTML. It's actually a HTML document. One is a folder, the other is HTML document. Download that. Okay, so let's go. Here we go. Do I have highlighted? Yes. I'm gonna right click, download, and it should end up in my download folder. Again, you know, make sure you go through those steps as well, so you know how to open it, how to download and open this document. You have your, oh, here you go. See, downloaded as a zipped folder, right? So in my computer, I go show folder, and your computer should be the same. It is in the download folder, unless you choose a proper folder in your computer, right? By default, it goes to the download folder. So what else? Now, whatever you will choose there is zipped inside this folder. You go inside, here you go. Next step. Locate the downloaded documents in your computer. It's usually in the download folder. I'm saying it's usually because depending how your computer is set up, might be downloaded elsewhere. Okay. It should be in a zipped format. Okay. Locate the downloaded document in zip format. Here you go. In zip format in your computer. It is usually, you know, it's usually downloaded to your download folder. You do that. Downloads, right? In the in the cell phone, it's gonna be a little bit different, right? In the cell phone. So now we are going to unzip the documents inside the zip folder. How do you do that? It's not that's easy. All you have to do, not this one here. All you have to do is to here you go. That's the folder, right? Go inside the folder, the zipped folder, highlight the two documents and copy them. Okay, so how do you do that? I'm gonna, here you go. Unzip the document. How do you do that? Go, here you go. Go inside the zipped folder. 2. Select the folder and HTML file and copy them. 3. Paste them outside the zip folder, anywhere outside the zip folder. Paste them anywhere outside the zipped folder. So I copy them. Oh, not here. So I'm gonna go outside the zipped folder, inside the download folder, paste them. Here it goes, pasting, let's see. Okay, now you have here, see that? The HTML file and its folder. They must, those two, they work together. They must be located in the same folder. Okay? Both, I'm gonna write that down. Paste them outside the zip folder. The HTML file and its corresponding folder must be located in the same folder of your computer. Don't put the HTML file inside its folder, its corresponding folder. Don't put the some students do that, don't put the HTML file inside its, what's going on here? Inside its corresponding folder. So let's go there. And now, all you have to do is to double click the HTML file. Okay? Can I display your information there, group 7? For the whole class to see? The whole class is gonna see it. Okay? Okay, so let's see here. Here you go. Yeah, right in here. I'm gonna zoom out. See Jennifer Camarillo, Alexis Nigret. Let's see here. For some reason I cannot zoom out. But the grade here is at the top. Let's see if I can do a view here. Let's see here. Zoom. Yep. It's not zooming. It's not zooming. Oh yeah, it is zooming. Okay. Okay, here you go. You have the grade there at the top. Any mistakes that you made are highlighted by a color. Okay. Here in this case, you had 2 significant digits, right? Group 7. You are supposed to show the volume with 2 significant digits. So you put two additional digits there that are not supposed to be there. Here the diameter was 3 significant digits. I was supposed to have 3 here as well. 3, 3, 3, 3. Okay? So I highlighted exactly what was not correct, right? Let me see if you missed anything else. Apparently you missed on the CL, because it's highlighted here. If you have any questions, you can come by and then we see what's wrong. And apparently that was the only mistakes. Okay, here, incorrect units. You had no incorrected units, right? Significant figures added. You added 7 significant figures on the total that were not supposed to be there. And there was 3 CLs that you didn't get it right. Subtract that, you get your final grade. Okay? So let me see here. Corresponding folder. Don't put the HTML inside this corresponding folder, okay? Double click the HTML file and you should see your corrections in color code. I'm recording that, okay? I'm recording that. Those are the steps. After you do several times, it becomes just second nature to you. Okay. So that's what happens when we save a document from Word or from Excel or from PowerPoint in HTML format. That's what happens. Okay. So they always create an HTML file and a folder that HTML file access the pictures, you know. So that they do. That's how Bill Gates decided to do it, right? There's another format that you can use too. I stopped using that format because some people was having problems with it. A simpler format, which was simpler. He didn't create the folder, a separate folder. But I stopped using it because some people with the Mac doesn't get it to work in his computer for some reason. But this one is universal, works well. Okay. Anything else? Okay, for today's and Thursday lab, I already prepared a video about the experiment. Okay? So when we go there upstairs today, the Tuesday group, I'm gonna tell you what the video is, and Thursday group you can also watch. It's like only 20 minutes long. Okay? I didn't have any equipment displayed there in the video, but I had the illustrations, PowerPoint drawings for you to orient yourself how to perform the experiment today. But I'll be present too, of course, right? But just by putting that video in there may save us some time in the lab upstairs. Okay, so let's take a look. Well, just go to my YouTube channel and I'm gonna see it there. Lab number 3. Number 3. Okay. Let me get some water here before I go. Okay, so here you go. That was what we did last time, right? That was what we did last time was relative velocity. Relative velocity. Let me get my PowerPoint as well. Here we go for stable vectors. No, not this one. Must be this one here. Let's see this one. Okay, let's see if I have a drawing illustration here. On the There's another way of solving that problem. Okay, which is the way. Oh, what's happening here? I didn't ask you to do that. Maybe I'm gonna do it here in the board. So that's how the book did as well. You can do either mathematically or you can do according to the way the book did. Right? So here you go. Don't forget that the point P with respect to B. So we have something like that. The ground referential A and referential B. Velocity of B with respect to A. Okay, velocity of V with respect to A. And then we have the airplane somewhere around there. The airplane is flying north. Their speed indicator on the plane indicates 120 knots. Okay, so the plane is tracking north. Let me see here. Okay, the plane is tracking north. Okay. The airspeed indicator indicates 120 knots. A ground station has measured the wind. Okay, the wind here is blowing to the east, right? Yeah, going to the east. Okay. North. The plane. And then what you end up having, you go VP of A is VP of B plus VB of A, right? So all you gotta do is, you have this right angle triangle. Okay, here is VP. Let's see. Let me see here. What's the ground? Okay, no, this is VP of B, and this VP of A. Okay. All you have to do is to look at this triangle and get the angle and the intensity and the velocity there, okay? So that's another way of solving this problem. Now, what you're going to do now is go to the next chapter. Sorry, couldn't get it. This one right in here. Enable editing. Okay. Laws of motion. Wait a minute. That's what I want. Choose the wrong one. Here you go. That's the one. Okay, here we go. And now we can start talking about that primary definition that we mentioned before. Okay, so here you go, laws of motion. That's the chapter we're going to talk about right now. Okay, so going back to the basic quantities, right? Length, time, what did I mean? What I miss here? Length, time, and mass. That's what's missing here. Primary definitions, position, right? And then you have the secondary definitions, velocity and acceleration. But then there is the second primary definition, which is the force. And that's the primary definition that we're going to start working right now on chapter 5. Okay, force. And then force is defined as what? Either a push or a pull. And I'm going to introduce you to the laws of physics. Three of the laws of physics. Okay, here you go. Position, force, push or pull. And I'm going to introduce you to those three laws of physics. So what we had here, let me take it out since I put it there. Right? I don't need that. Yeah, I'm just showing to you We talked about mass, right? We talked about mass in the lab, but not in the lecture. So here you go. I'm highlighting mass and the force push or pull. Okay, we're going to talk about Newton's first, second, and third laws. Let's start with the first law. And in the meantime, I'm going to get here my PowerPoint. Okay, so here you go. I have a slide here. Okay, so here you go. The one important force, let's talk about what forces are available out there. What forces that you need to know, okay? Let's try. Okay. Let us now talk about the laws of motion, which involve the idea of force. The first force that you have to know, first force you must know is the weight. That's the first force you gotta know. Okay, and the weight is defined as being the mass times the acceleration of gravity. Okay, so you have a push towards the center of the Earth. That's what the weight is all about. It's a push towards the center of the Earth. This object falls because it's being pushed towards the center of the Earth. Push, no, pulled. Pulled towards the center of the Earth. Okay? Push is something else, right? Pulled towards the center of the Earth. So that's the first force we have to know. Okay, and that's what is illustrated here in this slide. Okay. If you go ahead, have an object that's a little bit heavier than the other one, the force is gonna be twice as more massive than the other one. The force is going to be twice greater, but the acceleration is gonna be the same. The acceleration is gonna be the same. The acceleration is gonna be the same because of Newton's law, okay? And which I'm gonna introduce you to you soon. Okay, so but let's start with this one first. Which does not involve any acceleration. This one, those two here are examples of Newton's second law. Okay, but let's start talking about Newton's first law instead. That's the simple solution. That is the simplest example that you're going to see about Newton's first law of motion. Okay, you have an object sitting over a table at the surface. Okay, and it's at rest. In this case, it is at rest. Definitely, you know that there is a force pulling the object towards the center of the Earth, which is the weight. But if you had only the weight, this object wouldn't be at rest, it would be moving. So there must be a second force in there that's preventing that from happening, okay? Let me get that here. Here you go, this case, net force is 0. Here you go, weight, and then you have a second force called the normal, okay? So, first force that you have to remember, the weight, okay, is related to the mass and is related to the acceleration of gravity. And then a second force that you have to remember is the normal. It's a force between surfaces. And it is normal, it's called normal because it makes an angle of 90 degrees with the surface. Okay. So Newton's first law of motion states that if an object is at rest or moving with constant velocity, the net force is equal to 0. And that's an example of Newton's first law at play, whenever the object is at rest. Okay, so let's formulate Newton's first law. Here you go. Another force you must remember is a force between surfaces, a normal force. Okay. And then we can formulate Newton's first law of motion. The first half, first half of Newton's first law of motion. First half of Newton's first law of motion. Okay. Then we're gonna go the second half. If an object is at rest, the net force applied to this object is 0. Similarly, if the net force applied to an object is 0, now I'm gonna go further. Okay, the object will be either at rest or moving with constant velocity. Okay, the first half is the case of the object that is at rest. Okay, the second half is the case in which the object is moving with constant velocity. Okay, so I can go ahead and, if an object is either at rest or moving with constant velocity, okay, the net force applied to this object is 0. But it works the other way as well. If the net force applied to the object is 0, then the object is either at rest or moving with constant velocity. Can you memorize that? Okay, that's something that cannot be proven mathematically. That's why it's called the law. And then there are a bunch of examples for that. Okay, so here we go. That's one example. Okay. Oh, by the way, in the notes, okay, in a mathematical fashion, in a mathematical way, here you go, we do something like that. If symbol right in here, equation. Oh gosh. Okay. If v equals to 0, this implies that, net force is also equal to 0. And remember, there is a distinction between net force and one specific force, right? That's why here you go, net force is equal to 0. Those are vectors. Here you go. Get the vector there. And get the vector here as well. net force is equal to 0. But that's just just half of the whole thing, right? So if V is also constant, okay, the same thing holds. And it works both ways. It can go from here to here, but it can go from here to here as well. Similarly, if F net is equal to 0, it implies, if F net is equal to 0, it implies that the object is either at rest or V equal to constant. Like that. Newton's first law of motion. Stated also. So problems in mechanics is just a matter of identifying what the forces are in an object. Okay, and determine the state of motion of an object. So here we go, let's forget it. Okay, so here we go. Here's another example. An object is resting at the corner of a place, okay? So here we go. We have the objects at rest. Net force must be 0. Now the question is, what are the net forces acting in this object? We have the weight, you have this normal. If you apply a force from the left to the right, so we must have another force that's countering this F. Okay, and what this force is another normal, is a second normal force. You can go ahead and press the object against the wall. And the wall is going to prevent the object from moving by applying this force N2. Okay, and that's another example of Newton's first law of motion. Okay, another one, here we go, net force 0, weight, tension. Oh, you can also have the case of an object suspended by a string. Okay, an object suspended by a string. Just like this mouse. I'm going to make it stop oscillating, okay? It's at rest. So it has a weight that's pulling him down towards the center of the earth. But you also have another force that's called the tension. Okay, a third type of force. Let's document there. Here you go. Third type of force. Types of force. Weight. Normal. Tension. There are more. But let's stop here for now. Okay, net force is equal to 0, the object is at rest. What about this one here? The object is at rest, net force is equal to 0, we have a weight, we have a normal, do we have anything else? Yeah, we have F2, F1, and we have F2 that's countering F1. Okay, another example here. What about this one? There you go. Net force equal to 0, weight, normal, oh, tension. Let's say I attached a string to this object, right? If the object is at rest, there must be a force that's preventing the object to move to the left, okay? And this force can be, for instance, the force of friction, okay? The force of friction between those two surfaces. Now, oops, let's go back here. Now, note the following, this component of the tension here is working in conjunction with this normal force. So this normal force is actually being summed up with this component of the tension to cancel out the weight. Remember, this is a vectorial type of problem, right? We must have a horizontal component of the net force and a vertical component of the net force. Make sense? Okay? So in the fifth example, I can write like that. Here you go. I'm going to put in vectorial format. Fifth example. Oh, and we have, let's put here, force of friction as well. Force of friction. Okay. So here you go. Example 5 of the slides, right? Example 5 of the slides. PowerPoint slides. Velocity is 0. Net force must be 0 too. And what does it mean? Now is a question of being able to identify. That's the challenge, right? The challenge is identifying what are the forces, what are the individual forces that are acting in the object. In that specific case, the net force should be what? Should be the weight. I'm going to abbreviate by the letter W. Oops. Yep. What else? Should be the normal. Should be like a normal 1, I'll call it, right? That's how I call it. Let's go back there. Yeah, I call it normal 1. I didn't have to call normal 1. But that's okay. Normal 1. I'll use this one right in here. This is a vectorial equation, folks. Normal 1. What else? We know that there is a force, a tension force. So let's say there is a string attached to my object. And then we have this force 1 that can be a frictional force. Okay, which is still going to be 0. I'm going to put that in a different line. And let's not forget that what you see here is in reality two equations, two scalar equations. Okay, so we are going to have an equation along the x-axis. I'm going to do the like that. Here we go. A component of the weight along the x-axis. Here we go. So here we go. Net force in the x component of the net force. Okay. And I'm going to write down all of that in scalars now to make things simpler. Net, okay, that's gonna be Wx, and then we're gonna find out exactly what's the value of Wx. That's easy to figure that out. Okay, we're going to have a x component of the normal. We're going to have the x component of the tension. Okay. We're going to have the x component of this first one. I'm going to write that down. Let's figure x component of the first one. And then we can have the other components as well. The other component of the net force. You go y component of the weight. Okay, y component of the normal. y component of the tension and y component of the F1 force. Right? Now let's go back here to the drawing. Do we have a x component of the weight? Yes or no? No, right? Take a look. You know, if you put the x component as being the axis horizontal, there is no component for the x, no x component for the force, for the weight. Okay, so here you go. I'm gonna put 0 here. Okay, and we do already know that the y component of the weight is going to be minus mg, right? It's pointing downwards. I don't want to do that. I want to do in the next one. You go, so you don't lose this information, right? It's a little bit more extensive, but here you go. Now we got it. Yep, here you go. This one is going to be 0. What about this force here? Does it have a y component? Yes or no? Take a look at the drawing. Does the F1 has a y component? No. And what about this normal one? Does it have a x component? No, right? So N1 has no x component, F1 has no y component. Okay, N1 has... I should have put here 1. Yeah. 1 comma. 1 comma. Right? There is no x component for this N1. I can put it 0. But we do have a y component for N1. F1 has no y component, so we can make it 0. Okay? So that's the type of equation that we have to solve. And here, don't forget, we can put minus mg. Minus mg. Okay? That's the type of solution that you have to worry when you solve problems like that, either at constant velocity or at rest. It's 5:48 right now. Let me see if I have any more before we go to a break. Here you go. Let's see this one here. Now velocity constant. Okay? V constant, net force is V constant as over a frictionless surface. Net force must be 0. So we must have, we always have the weight in there. So we must have another force that cancels with the weight. And this force is going to be the normal. Since there is no friction there is no need to have forces in the horizontal direction, right? Unless you apply a horizontal force to this object that's moving with constant velocity. Okay, here you go. In this case, now it's Newton's second law, okay? Net force is not 0. So let's go and take attendance here and go for our break now. Daniel Abraham, are you there? Good. Next, Mario Acevedo. Good. Harun Atif. Musa Atif. Genesis Bell. No. Jennifer Camarillo. Vincent D'Aloisio. Okay. Robert Faust.
Here.
Next is Pedro Flores. Here. Lawrence Flores.
Here.
Alexander Garcia.
Here.
Yeah, okay. Sung Ham, what's that there? Okay. Brian Herrera. Nope. Brian Nis.
Here.
Athena. There. Jesus Lepp. Cassandra Martinez. Dylan Martinez. Henry Martinez. Leonardo Melga. No. Rafael Mercado. There. Okay. Raymond Miramontes. Good. Jaime Mondragon. Alexis Nigret. Yahia Paris. Nope. Marco Antônio Partida. Armando Pérez. Abraham Pérez. No. Nicolas Pisano. Okay. Hans Buster. No Hans. Ramon Quintana. Next, Albert Ramirez. Ali Sharabi. Okay. Amna Sieda. Amna. Okay, not here. Dave Sompaxley. Not here. Antonio Vega. Ken Villagomez. Patrick Villavazov. Nolan Williams. No. And we have. Okay, let's go for our break now. It's 5:51. Okay, so we go 6:06. Break.
Yep. The other example, I didn't catch it. The other one.
Let's see here. It was constant velocity. Constant velocity. Well, there's a problem with this one. Okay, net force is, yeah, it cannot be constant velocity, right? Because net force is not zero. I gotta fix that.
Okay. The other one, the other slide, Prof, the other one with tension. The
The
tension.
tension, let's see here.
There goes the other.
It should be in the.
That one. That one.
This one? No, no, that's not. Oh, yeah, this one is the tension. Yeah,
Can
that's
I take
right.
a picture real quick and then you can show
Sure,
me?
it'll be in the video there that I'm gonna post. Uh-huh.
So can you still upload the notes? Cause
Yeah, you mean the written notes?
yeah,
Yeah, I gotta do that. I stopped doing that. But you have the videos there, you know, on my YouTube
it's a bit easier for me when I have
for
like
the
a
notes,
doc.
right?
Yeah.
Okay. So let's see. Let me do it right now, so I don't. But remember, I stopped. I stopped documenting everything in the notes, right? That's why I lost my motivation to continue uploading the notes. Let's see. I'll do that right now. Reading is much more efficient than
Yeah.
watching a video, right? But some people prefer a video.
Sometimes it's best to have like pen and paper.
Yeah.
And as for the PowerPoint, like, could you upload those as well, maybe?
Well, the PowerPoint you gotta get from the video.
Oh, okay, that's
The
fine.
PowerPoint I consider that proprietary.
That's fine.
Okay.
Thank you.
Okay. So just fast forward to the video now. Man, it takes forever. I don't know. It takes forever. Okay, let me stop this guy here. I'm gonna pause him. So here you go. Because the velocity is constant or zero, the acceleration is gonna be zero too. Okay. So that's the important thing about the first law of Newton. And here are some solutions. The first case in which you have the object resting over a table, the weight is equal to the normal is equal to minus the weight. Is the vector, and that's what we are gonna let's go back here in the notes that I was solving. Right, here you go. Here you go. We had this situation here. If you know, let's go the next step here. Okay, if you know the force 1 being applied over the object in that example, then you can find out what is the x component of the tension. Okay. Okay. Similarly, in general, you know the weight, right? And if you want to find out what's the normal one, what is it going to be? The normal is going to be mg minus the y component of the tension. Okay. In that example that I showed to you. Compare that with the other case. We are talking about this what I did in the notes. We are talking about this one here, this case. Okay, so compare that with the case in which the block is just by itself. This one, right? Not this one. Not this one, the very first example. Here you go, this very first example here. In this case, the magnitude of the normal is going to be exactly equal to the magnitude of the weight. But if you add another force along the y-axis, just like in the other example that you saw, now the normal is no longer going to be equal to the weight. It's going to be slightly less in that case. Okay? And in that case, it's going to be slightly less. So here you go. In this specific case, this normal here is going to be less than the weight. Less than mg. Because you are subtracting a y component. Okay? So you have problems, also all those types of problems for the, Newton's first law. Let's see if we have another interesting one here. Here you go. The book already also have, let's see, the case. Figure is another example. That's an example in the book. Let me see here. No, that's an example in the notes. Okay, that's a figure 5.2, right? That's the case of figure 5.2. It's another example. We have all sorts of examples involving Newton's first law of motion. Okay, here we go. And we have this other one here. That's 5.2. Let's see, 5.3. Slightly more complicated. Okay, you saw that in the drawings, right? So here you go. So take a look here. You have the weight and you have the normal. Since we have a tension here being applied upwards, this component of the tension is summing up to this component of the normal. So when you solve this problem here for the normal, this normal alone is going to be less than the weight. Okay? Just like you saw before there in the notes. So here you go. Okay. So that's first law of motion. For now, you have to memorize that. Okay, another way to formulate Newton's first law of motion is to say that if the acceleration of an object is zero, then you no longer have to say that velocity is zero or velocity constant, okay? Then net force applied to the object is also zero. That's another way to formulate Newton's first law of motion, okay? It means exactly the same thing. So let's copy that and paste in there. Another way to formulate Newton's first law of motion is in terms of the acceleration. Or how is that? Here you go. If acceleration of an object is zero, then the net force applied to this object is also zero. Then the net force applied, and vice versa. And acceleration zero can be either object at rest or moving with constant velocity. Save it. Now let's go for the second law of motion. Okay, how do you formulate the second law of motion? You should know that already, right? Second law of motion. Here you go. The net force applied to an object is mass times acceleration. Okay, remember, it took like hundreds of years, if not thousands of years, for us to come up with this formulation. Net force applied to an object is mass times acceleration. And then this can be three scalar equations. Here is just one single vectorial equation, but in reality, you have three scalar equations. You can have the x component, the y component, and the z component. Okay, remember that. And now that's when we figure out that the first law of motion is nothing but a special case of the second law of motion. Why is that? Because if the acceleration is equal to 0, the net force is going to be equal to 0, right? So we say that the first law of motion is not a law. It's not a law at all. The first law of motion is actually a corollary to the second law of motion. It's a consequence of the second law of motion. So strictly speaking, first law of motion is not a law. Okay, physicists has the habit of giving names to laws which are not laws. Okay, so let's write that down here. But we do that because we want to honor Galileo Galilei, who studied this law before, this relation before Newton himself. He didn't quite get it right, but he took us in the right direction until Newton came to the exact formulation. Okay, here goes Newton's second law of motion. Newton's second law of motion states the following. Ooh. States the following. Okay. I'm gonna copy and paste it. Here, I'm gonna do that. Copy this one. No, I want this one here. States that the net force applied to an object is its mass times its acceleration. Okay? That's what you have to memorize. Okay, note that if A equal to 0, if the acceleration is equal to 0, i.e. object at rest, or moving with constant velocity, net force is equal to 0. In reality, we can get Newton's first law from the second. Which means that the first law is not a law at all, but a consequence of the second law. We also say it is a corollary to the second law. A corollary to the second one. Or you can even call it a theorem as well. Or a theorem. Different words that mean the same thing. And go. So that's, let's take a look at the notes. Okay, what's the unit of the force? The unit of the force is the kilogram times, according to Newton's second law, the unit of force is the kilogram mass times mass, kilograms meter divided by second square. Unit of mass times the unit of acceleration. And that we call the Newton. So it is the second law that tells us what exactly are the units, what exactly is the units of force. Okay, the Newton itself is equal to kilogram meter per second square. That's what we are doing, dimensional analysis. Okay, so let's do that. This one here. An object of known mass. Yep, here you go. of no mass is resting over frictionless surface and moving in the horizontal direction. Two known forces are applied simultaneously, F1 and F2. Here's an example. At angles shown in the figure. Not in the physics, in the figure. Determine the magnitude and the direction of the acceleration of the mass. Determine the magnitude and the direction of the normal force. Okay, so here you go. Let me see if I have that in my PowerPoint. Let's see. Doesn't look like I have any PowerPoint. Yeah, unfortunately I don't. Yeah, I don't have it. Okay, so let's do that together. Okay, so I'll copy this drawing here, right? And paste that in my notes. Example. There you go, that's the situation. Oops. Okay, those are the force 1, force 2. Okay, so the first question that you have to ask is the mass accelerated along the vertical direction? That's the first question you have to ask. Okay, is the mass accelerated moving along the y direction? Yes or no? Take a look at the drawing and then the information that was given, right? The information that was given was that the motion was only along the horizontal direction, right? Here you go. Moving the horizontal direction. There is no motion along the vertical direction. So right from the bat, you know that the y component of the acceleration along the y direction is going to be what? It's going to be what? What's the y component of the acceleration in the vertical direction? It's going to be 0, okay? It's going to be 0. So it is Newton's first law of motion that applies in the vertical direction. Okay? So let's get the equations of motion in the vertical direction first. Because it's easier, right? We're getting the equation in the vertical direction, the equation of motion in the vertical direction because it's easier. Okay, so here we go. Net force is MA, and then it can be broken down. Net force in the x direction, acceleration in the x direction. But because I'm taking the components now, I don't need to use the vector symbol anymore. It can be a scalar. Okay, it's not going to be net. It's two-dimensional motion, so I don't have to worry about the z component. Okay. And then we're going to worry about the actual forces. Just remember, right? Every problems of forces involve identifying the proper the forces. Any problem that involves Newton's law of motion, requires you to identify the forces, each of the forces that are acting in the object. That's the tricky portion of Newton's law. Here you go. There is no acceleration along the y direction, but there is an acceleration along the x direction, and that acceleration, just call it A. Okay, we should know. Let me see if I told you what the mass is, right? Yeah, object of mass m. So mass is known, the forces are known, and the angles are known as well. Determine the magnitude and direction of the acceleration of the mass. Okay, so let's the acceleration of the mass we can get from this equation here. But first we have to identify the forces in the x and y direction. Go 0. X component of the forces. F1 cosine theta 1, F2 cosine theta 2. They are both in the same direction. And by the way, they are also in this, because they are in the same direction, the direction of the acceleration is going to be their direction as well. F1 cosine theta 1, F1 function cosine theta 1, F2 cosine theta 2. F2 cosine theta 2. Here you go. And in the y direction, what do we have? We have the forces. F1 is downward, the y component is downwards, the y component F2 is upwards. So you go ahead and write down. Okay, that's gonna be 0 here. I'm gonna go minus F1 sine of theta 1 plus F2 sine theta 2. And we're gonna have also minus mg, which is downwards. And then we have what? Plus n bigger, like that. That's gonna be 0. But the problem is asking the acceleration. Let's worry about the second equation later on. Item A, the acceleration is, there is no negative sign there because the forces are to the right. Equal, that's the acceleration. Okay. That's item A. Let's see item B. Determine the magnitude and the direction of the normal force. Okay. I know theta 1 and F1. I know theta 2, F2. I know mg. So it's just a matter of solving for the normal now. Okay. So normal in this case is going to be, change the signs, right? Minus and plus. Okay. So here you go. Let me give you another example here. In this case, the normal is equal to the weight. Okay? In this case, the normal is equal to the weight. Now, suppose that I apply a force from the top of my bottle. So what happened to the normal now? The normal now increased. Okay? Now, if I were to try to, raise the bottle, but not quite raise it completely, now the normal is less than the weight because I'm applying an upward force. Okay? That's the simplest example that I can give to you. Okay, here you go. I'm applying a downward force here, the normal increased. I'm applying a normal force, I'm applying an upward force here, the normal decreased. Can you picture that? Okay? One-dimensional problem. And that's what's happening here in this case. Any questions? What time is that? 6:34. We have a little bit more of time. Here we go. Third law of motion. The third law of motion is the one that's a little bit more difficult to understand. Okay? And that applies not just to mechanical objects, but also to microscopic objects as well, at the microscopic level. Think about that. This thing was, what you see right in here, was formulated by Newton. Let's see, back in the, 1600s, right? Let's take a look when Newton formulated that. No. Okay, here we go. Newton's, Isaac Newton, right? Here we go. When did he? So he was born in 1642 and died in 1726. Okay, so the laws of motion must have been formulated in the 1600s. Okay. By then, electricity and magnetism had not been formulated yet. But when it was fully formulated, the scientists discovered that those three laws of motion were also being applied to the macroscopic world in electricity as well. Those are the hallmarks of a successful theory, okay? So you formulate something long time ago that applies to one thing, that applies to a mechanical object, and let's say 100 years, 200 years later, you come up with another description of nature that relies not on mechanical objects, but relies on microscopic objects at the electrical realm, at the magnetic realm, and you discover too that those same laws that were formulated 100, 200 years earlier for macroscopic objects also applies to that new science that you're discovering. Okay, so those are the hallmarks of a successful theory. And you're going to see in Physics 38 that all those ideas here can be applied to electricity and magnetism. And the next law of Newton, which is the third Newton law, it's a little bit more difficult to understand. Let me see if I have an example here for you. It involves the interaction between two objects, right in here, from current slides, okay? So you have two objects. You already know that your mass has a weight, right? You already know that your mass has a weight. Let's see. Yeah, here you go. But where this weight is coming from? This weight is coming from the gravitational attraction of the Earth. Okay? So what does it mean? It means that the Earth is interacting with this small object. And by interaction, we mean Earth is applying a force to that object. That's what interaction means. Okay? So Newton's third law of motion, what does it say? Newton's third law of motion states that if two objects interact among themselves, okay? Let's say object 1 applies a force to object 2. What does it mean? It means that the object 2 is also going to apply a force to object 1. And this force is going to have the same magnitude but opposite direction. Okay? That's what you have to know. And that memorize that, you know, if two objects interact with one another, if object 1 and 2, if object 1 applies a force F1 in object 2, then it means that object 2 is applying an equal force with opposite direction. It doesn't matter if it is a small apple, the force is going to be the same. The Earth is not applying a larger force on the apple. No, the Earth is applying a force that's equal to the force that the apple is applying to the Earth. This sounds counterintuitive, right? How come a big object can produce the same force that a small object is producing? That sounds counterintuitive, right? But that's exactly how it is. Okay, this mass here is filling a weight of, let me see, is 1 kilogram more or less. No, it's not 1 kilogram. It's 250 grams. Okay, 250 grams, 0.25. It has a weight of 2.5 newtons, more or less. This bottle, okay? That's the weight of this bottle. 2.5 newtons. The Earth is applying a force of 2.5 newtons in this bottle. 2.5 newtons because we have only half of the bottle. I drank half of the water. Okay? So what does it mean? It means that this bottle is also applying the same force on the Earth. This bottle is applying a force of 2.5 newtons on Earth. Okay? This small object is applying the same force in the bigger object. It's counterintuitive, but that's the way it is. Okay? The question now is, what is the effect of the force that this small object is applying on the Earth? Okay? What's the effect? The effect of a force is what? A force leads to an acceleration, right? According to Newton's law, right? F equal to ma, right? But because the mass of the Earth is much greater than the mass of the apple, the acceleration of the Earth due to this apple alone is going to be much less. Okay, that's where the key difference comes. The force is the same, but not the acceleration. Not the acceleration produced by that force. The force that is exerted on the apple is mg, which produces an acceleration of 10 meters per second square. The force that the apple produces on the Earth is also mg, but the acceleration is going to be much less because the mass of the Earth is much larger than the mass of the apple or the object. Do you get the idea? Okay? So here we go. So that's what Newton's third law of motion is all about. Every problem you will have to identify whether you have to apply Newton's third law or not, especially if you have two objects interacting with one another. If two objects 1 and 2 interact with one another, they exert forces on each other. Okay? Newton's third law of motion states that the force that one exerts in 2 is equal in magnitude and opposite in direction, compared to the force that 2 exerts in 1. Okay, the force may be the same, but the acceleration, no, may not. The force may be the same. The force is the same, not maybe. The force is always the same. It's always the same between interacting objects. However, their acceleration may not, because, however, if their masses is different, however, are different, the acceleration are not. For instance, case between, an apple and Earth. Okay. Apple has mass m, apple of mass m, and Earth of mass capital M. Okay. The Earth exerts a force mg on the apple. Okay. Consequently, according to the third law, the apple exerts a force mg on the Earth. The forces are the same, but the acceleration resulting from these forces are not. Okay, for the apple, A is going to be equal to G. For the Earth, acceleration of the Earth is going to be what? It's going to be the force that the apple exerts on the Earth divided by the mass of the Earth. Okay? mg divided by big M. And where big M is much greater than small m. Okay. What time is that? 6:45. Okay, any questions about that?
Professor,
Yes.
was actually Isaac was the one that actually because I did hear a story when he was actually was underneath a tree and then an apple actually hit on his head and actually he actually found out how did he
Yeah, that's what
done the
they say.
experiment. Yeah, that's what
Uh-huh.
I heard about him more
Yeah,
than
that's right. That's what they say. Uh-huh. I think it's more like a myth than anything else. The story has more to do with the fact that Newton's parents,
right.
they had a business, an apple business.
Oh, I didn't know that.
Okay, and then they
Right
came
off.
up with this story just to propagate the fact that his parents were in the business of growing apples and selling apples. So there was a.
But he was also working with someone else too, no, to figure out the formulas.
Um, I don't think so. I think Newton. He had this habit of keeping everything secret.
Mm-hmm.
Okay, so much that one of his major contributions he kept a secret for 20 years. So I believe that he derived all of that on his own, with of course, the help of other people that came before. Okay, what happened to Newton is that he kept the theory of universal gravitation to his own for 20 years, and then one day this guy came to him, Edmund Halley, his name. Okay, he came to him. Look, we have this comet that comes about around the Earth every 80, 90 years, right? Can't you? Is there? Do you think there is a way to predict the comet's appearance? In the future, right? And then Newton came to him. I know how to solve this problem, right? You know how to solve this problem? Oh yeah, I did that 20 years ago. Okay. And then Newton cranked up his formulas based on the position of that comet that passed nearby Earth several years ago, right before his time. And he came up with a prediction, and that comet became known as the Halley comet. It was Halley now who proposed the problem to Newton, but Newton calculated the appearance of the comet. It was Halley who got the credit for the name of the comet. Okay, the most famous comet that we have, right? So yeah, I believe that Newton, did that on his own because he used to keep those things secret. Okay, he had a conflict with another guy, Leibniz, for the invention of calculus, and he didn't work with Leibniz. They invented calculus independently from one another, and then Newton went after him and persecuted him for plagiarism. Okay, when in reality Leibniz himself did that work on his own, and he used a notation that was far superior to the notation of Newton. Newton was using, the derivative notation of Newton that he was using was the dot. Everybody learned that in calculus, right? That's the notation that Newton was using to denote derivative. Leibniz instead was doing this notation. So this notation is far more superior than this notation here. Okay? The notation on the right is far more superior because it has far more information than this notation right in here. And Newton accused him of plagiarism. Okay. When in reality his formulation was superior to Newton's formulation. It was Leibniz, right? Leibniz, and this is like that, Leibniz and Newton. Okay, so it's 6:49 now. Let's go upstairs if you're taking. And we are set, right? We can do the exam in that way that I mentioned, right? Everybody's okay with that? I thought I had, I remember sending an email to everybody. I do not know, but it doesn't look like you got it. But I will send it again.
Professor?
Yeah.
So can I just check which email that you send it to
Uh-huh.
for me? Because I don't think I received your email.
Okay, so it looks like nobody received it, right? So I'll have to send it again.
Okay, thank you.
So maybe I forgot to send it. I wrote the email. Maybe I forgot to click the send.
Okay,
Maybe
yeah, that's
if
fine.
nobody sends, so I'll do that again.
All right, thank you. Have a nice evening.
You too. Okay.
Oh, Professor?
Yeah.
I have a question on the homework.
Uh-huh.
How do you call it? When I'm doing the assignments,
Uh-huh.
there's a button right on the right hand side where it says ask the teacher.
Uh-huh.
Do you get like a notification if I click on it and let
Yeah.
me see if I'm stuck with the problem, or how
Yeah.
does that work?
Yeah, I don't usually go to WebAssign. So if you have a question
Mm,
about, send me a regular email to
mm,
my personal email address
okay.
because I don't usually go online to check those questions. Okay, yeah, I do get, but I don't usually log into WebAssign to see if there is any messages there. It's easier, if you have a question, it's easier for you to send me a email to my
The email's that problem and how
yeah.
to solve the
Yeah,
situation.
preferably to my personal email address because this is one personal email address I'm checking all the time.
Okay.
Okay.
All right, sounds good. All right, thank
Yeah.
you.
I had one more question.
Uh-huh.
So just to kind of recap what you said about the test.
Uh-huh.
So we start on the 7th of October,
Uh-huh.
and then we have a 24-hour period.
7
So
p.m.
as soon as we start, we have to complete it.
Yeah, you have to complete in one sit in 2 hours.
Okay.
You
What's
have a
that?
window of 24 hours.
Okay.
Okay, but you have to allocate 2 hours within that window. Okay, you cannot break it down in half an hour window. You cannot do that.
So
You
once I
sit
start,
on the start. You have 2 hours.
okay.
Okay, you gotta finish it.
Okay. So once I start and then finish it, so I have from the 7th. So technically, I still have until Friday, right, for the 24 hours.
Yeah, yeah. You should have until Friday, 7 p.m. to
Friday, like
7 p.m.
7
Yeah,
p.m.
yeah. You can allocate from 7 to 9 p.m. You can allocate from 9 to 11. You know.
for the next day, which is
Yeah,
Friday,
you can even do it 1 o'clock in the morning. If you
up to
one
any.
to three, okay, you
Okay.
can 7 o'clock in the morning until 9 o'clock in the morning the following day.
Okay.
Uh-huh.
And the test is. I know you can't give me too much, but the test is gonna be based on like what we're learning in class, or
Yeah.
is it gonna be more towards like the homework?
Oh, towards the homework and what we did in class as well.
Okay.
Okay.
Okay, bro.
So there, use the notes as a reference, use the book as a reference, use the homework problems as a reference, and we use the examples as a reference.
Okay.
All those four.
Okay.
Okay.
Thank you.
Okay.
See you up there.
See you. Bye. You don't need to do that now.